Hi, I'm Xiao from the National University of Singapore. I'd like to present our work, Learning Latent Graph Dynamics for Deformable Objects Manipulation. The robot manipulation has been successfully applied to different tasks, for example, like autonomous driving, warehouse robot navigation, manipulating rigid body objects, and flying a drone. One special characteristic shared by these tasks is that they have a very well-defined state space. But this doesn't always exist in the world. Consider tasks like pouring water, feeding a kid, folding cloth, and also like making my favorite noodle. So these tasks, they remain very challenging for the robots. We think the major difficulty here is that the large degree of freedom, when coupled with the nonlinear dynamics, will make the modeling of the dynamic model and also playing with it very difficult. So in this work, we take a different view. For objects like cloth and ropes, their dynamics can be sufficiently captured by a set of the key points. So this is similar to how humans manipulate cloth. We only consider the key point, such as the shoulder, the collar, and etc. We don't consider the full dynamics of the object because it's not necessary, and our brain doesn't model it. So the key points can be further grouped into a graph, where the edges further capture the key point interactions and further improve the performance of the model. So in this work, we introduce GDOM, graph dynamics for deformable objects manipulation. GDOM performs unsupervised key point detection directly from a top-down depth image. It extracts key point features, groups them into graphs according to the spatial relationships, and reasons a learned latent graph dynamic model for decision making. Specifically, we use graph neural networks to capture the interactions among key points. A graph-based model predictor control is introduced to improve the quality of the and sample efficiency of the planning. To effectively learn a dynamic model, we aim to predict the next state and minimize the difference between the predicted state and the encoded state directly from the images. Contrastive learning is further used to improve the quality of the learning model by contrasting the positive sample, which is the predicted state, with a bunch of the negative samples that are irrelevant and sampled directly from the dataset. We train a model in simulation with randomly sampled reactions and show that the trained model can be generalized directly to a real robot without any fine-tuning. We show that our model can successfully straighten and reposition the rope to different orientations. For example, like here, we reposition it with a degree of 0, 45, 90, and 135. We also show that the model can be used to flatten a piece of crumpled cloth with different sizes and also fold them. Qualitatively, we show the results in the previous slide, and quantitatively, GDOM significantly outperforms the state-of-the-art models on all rope positioning tasks and also cloth manipulation tasks by a large margin. In addition, we show that now the model can be transferred directly to a kinetic robot with only simulation data. We mount a top-down camera, that is the Kinect, to generate the depth images. So here is a short demo video of the results. In this video, the bottom right corner shows the detected key points. Our trained model successfully straightens a rope and repositions it with an orientation of 45 degrees. In addition, it is also able to flatten a piece of cloth with only 4 steps of actions. And here are some additional visualizations of the detected key points. So the key points are visually salient on both simulation images and the real-world images. However, there are also some failure cases. The number of the key points has to be carefully chosen. It might be noisy given the extreme deformation of the object. The inaccurate detections introduce additional noise to the model, but with the contrastive learning, the learned dynamic model is still robust. Thank you for listening. More details are available in the QR code. Thank you.